This early morning session, we have Brando Bellazzini. You say something, Brando?
Yeah, I'm here. I'm trying to share the screen. Okay. Can you see my screen?
Yes, looks good. Okay, so we're happy to have Brando. He's going to talk about causality and gravity and the self-stress of photons. Please take away, Brando.
Okay, so thank you very much for the invitation to this meeting between gravity and QCD, which is such a terrific program. And I will tell you about aspects of causality in gravity, and I will use scattering of photons to investigate this. And this is going to be based on this work I've done with my student, Giulia Isabella, and with Matt Lewandowski and Francesco Sgarlatti. So I think it's fair to say that causality in quantum field theory is rather well understood. And since the very beginning, in fact, of quantum field theory, one of the greatest success, in fact, quantum field theory was the prediction of antiparticles. And that was coming straight from requiring that observables that are space-like separated should commute, and that's require introduction of antiparticles to be achieved in our relativistic quantum field theory. And we have seen that such foundational aspects now has also implications which are much more practical. We have seen these two talks from Francesco and David, where we can derive positivity bounds on effective field theory coefficients that you can measure at low energy, things that we care, and they come again from causality that translates to analytic properties of the scattering matrix together with unitarity. Now, the situation with causality in gravity instead, I think, is less understood. And I think it boils down to the fact that the causal structure, which will be set by the metric of space-time, is itself fluctuating as a quantum observable. And this is basically a statement that you have a lack of local observables. So this, I think, brings me to consider in the following, if I want to make some progress, some statement about causality and gravity, to consider quantities which are well-defined, even in the context of gravity, and we focus on the S matrix. And causality is a statement about regions of space-time and whether they can be connected by particles moving from one region to another region. So I think it's very natural to try to express them in terms of basically how you reach the cluster decomposition, where you consider two clusters of particles which are separated spatially. And you know that if they are spatially separated, the farther away they are, the closer to a factorized amplitude you should get. And that's the leading term that you get in a scattering amplitude. The statement about causality is a statement about the subleading behavior. So it's a statement about how the amplitude should behave, except for the exact factorization. And this behavior is not going to be exponentially suppressed unless you have a particle that on shell can propagate from one cluster to the other cluster. And we are very familiar to this property in the relativistic limit, the potential theory, when you consider potential between particles which are separated more than the quantum wavelength associated with the carrier of the force, which is exponentially damped. In the relativistic settings that I'm interested in, this means that working with amplitude, the very good thing to think about to express this notion of separation of clusters is to work in the impact parameter space, B, which we're going to use to dial the separation between the particles. And moreover, we're going to work with the focus on gravity effects. So I'm going to work also the Transplanckian limit. So when the center of mass energy S is larger than Planck squared, so GS, the gravitational coupling is very large. Or you can also consider large backgrounds. Moreover, to simplify the most possible the situation, I'm going to consider 2-to-2 scattering amplitudes. So it means that the two clusters are just two particles which are very far, and I'm going to assume that they interact only through gravity. And so the most important object here that will characterize the system is going to be the matrix element of the energy momentum tensor when gravity is exchanged between the two particles. And the first two properties, 1 and 2 here, large impact parameter, so large separation between the two particles, and large central mass energy, Transplanckian energy, means that I'm going to consider a conal Transplanckian scattering. Okay, these particles are very energetic, so energetic that gravity is the main effect, but nevertheless you have control because they are very fast. They are separated in the impact parameter. And so the scattering angle in particular is going to be small. You have a expansion parameter that's the deflection angle itself. So it's useful to recall here the lengths that are at play here. So the smallest of all is going to be the computative wavelength of the scattering system, which is 1 over square root of s. There's going to be smaller, much smaller than the Planck length because I'm working in Transplanckian scattering. And the other relevant scale here is going to be the Schwarzschild radius of the scattering, which is given by g Newton times square root of s, which is much larger by the Planck length, and that's good because it's going to give me control over quantum gravity effects, which I will not be able to control otherwise. So B, as long as it's taken very large relative to this scale, means that I have a small parameter in this theory that I can use to organize my calculation. It's given by Rs over B, so the Schwarzschild radius over B, or lambda Planck over B. Okay, and this in general, this is going to be much smaller than Rs. So by dimensional analysis, this parameter here, Rs over B, is the most important. And as a matter of fact, Rs over B controls the scattering angle. So this is basically an expansion in the scattering angle. And this means that when you consider S matrix in the impact parameter space, you organize the scattering phase in terms of insertion of G Newton. It's actually better to think about them as insertions of powers Rs over B or lambda Planck over B. Now, in fact, many of the scales can appear in the problem, and in general, they do appear. If you have like a weak couple or a weak completion for gravity, you may have lambda strings that can be actually larger than Rs, for example. Or you may have standard model contribution, and just to have in mind some values of the parameters here. Just let's imagine that I'm scattering with an hierarchy between the energy and the M Planck to be about a factor of 10 to the 3, so 3 orders of magnitude. And that's the same hierarchy between Schwarzschild radius and the Planck length. And you see that there is a huge window. It's a huge window here between Rs and the scale, for example, of the standard model, where I can fit some new effects. And essentially, even if these are weakly coupled to the system, basically just by dimensional analysis, the ratio that actually will matter most will be lambda S over B, because it's going to be the largest of all these ratios. So in fact, that's what I'm going to focus in the following, is the case where I'm going to consider a single G Newton, the leading effect is going to be given by a single G Newton insertion, and then I'm going to consider the correction coming from any other scale that can appear here in this huge window. And these corrections are definitely much smaller in many instances. And so you're going to have one gravitational exchange, and I'm going to consider a system where some particles here that are going to be photons later on scatter against some spectator that interacts only gravitation. And could be for the order and working can be the graviton itself, like can be any other spectator particles. I'm going to consider it also massless for simplicity. So it's going to be an expansion of this type. So you have a large coupling in front, gravitational coupling. Then you have this is going to be the universal leading econal contribution in 4 dimensions as a logarithmic behavior in B. And then there are corrections coming from these scales over B. And for example, the activity of photons, if I scatter photons against some spectator, in the limit where B is very large, I can organize this as an effective theory. And in addition to the minimal coupling to gravity, I can add some non-minimal coupling to gravity of this type. And this alpha 3 indeed is dimensionful, is going to control this scale lambda nu prime, lambda new physics. And I'm interested to see what Causality has to say about the properties of this type of operators. Before moving on, let me open one parenthesis very super quickly. This is very closely related to scattering actually astrophysical bodies. So I'm interested in scattering particles at Planck energy, but if you scatter stars, they are definitely Planck also, and if the impact parameter is much larger than the radius, they basically fulfill all the assumptions I was making. The main difference is that, of course, the microscopic scales are all super tiny relative to the Schwarzschild radius, which could be order of kilometer, for example, for our sun. It seems in that case, only the Bose-Minkovic expansion actually makes sense. But not quite. In fact, if the astrophysical body has a size, you can resolve it. As you approach it, you start resolving its size. It's a microscopic structure. It's not going to be microscopic physics as a particle physics would think of it, but it's definitely going to be a correction you can capture again as an effective field theory point of view, as it was done, for example, this paper. There are many follow-up papers which are super interesting. That said, let me move to now scattering particles, particularly photons, transmagnetic energy, and large separation, against some spectators that interact only gravitation. And as I said, I'm going to consider the leading effect coming from a single graviton exchange. In this case, the scattering phase is given by the Fourier transform, the two-dimensional Fourier transform of the one graviton exchange amplitude. And when the momentum exchange is very small, the impact parameter is very large, you don't resolve the structure of the energy momentum tensor that controls this interaction, that it collapses to a point. And moreover, since we're interested into the large B limit, large separation, what matters here is actually only the non-analytic terms. Things that's analytic in Q, the momentum exchange, Fourier transform gives you a delta function or derivative of it. So it doesn't matter. And what matters are only the non-analytic parts that, when these collapse to points are given by just when these particles are all on shell. So the full physics here, large distance, is captured by on-shell 3-point functions. Okay, there are just two of them. The helicity preserving plus minus for the photons and the helicity flipping plus plus for the photons in 4 dimensions. And they are in one-to-one correspondence with, this effective action for the photon is the minimal coupling from the kinetic term, this irrelevant deformation that give contribution to helicity flipping. So now the scattering matrix is a matrix also in the helicity index here. You can take plus minus, helicity preserving, or plus plus, and its Fourier transform gives you the scattering angle. The scattering phase, which is coupling constant, gravitational coupling constant GS, large, the logarithmic behavior coming from the minimal coupling. And then, importantly, there is a contribution coming from eliciting flipping 3-point functions that scales like alpha 3 over b squared, which is not positive definite. So regardless of the sign of alpha 3, there's always a choice of polarization for which these have opposite sign of the log. This is going to be important for causality. Why is that so? Because the scattering phase controls various physical observables, among which the one I'm interested today is the time delay, which is basically how much you have a photon coming by, is scattered against this mediator. Along in the scattering process gets delayed by a certain amount, delta t, relative to the straight trajectory it would have had without interaction. And that delay is the derivative of the scattering phase we just computed. It's relative to central mass energy. And because that was linear in S, that's proportional to delta itself. So the sign of delta at this order determines the sign also the time delay. Now, the condition of causality that I'm going to use, the following, that we have been calling asymptotic causality in our collaboration, is the requirement that this time delay should always be positive. Basically, it should always be delayed, or it should always fall inside the Minkowski light cone. You cannot propagate signal outside thanks to interactions. And of course, this, in order to make sense, you have to require that this is large enough relative to the quantum indetermination, so to the localization of the wave packet. And this basically for a scattering phase that grows linear with S, it just says that the phase must be large. But that's okay, because that's precisely our situation where we took a large coupling constant to begin with. So now you see that this condition, causality, asymptotic causality, may be violated in principle if you are allowed to lower B. So regardless of the sign of alpha 3 that controls the triple function for helicity flipping terms, there's always a choice of helicity for which if you lower B, eventually this term would overcome the minimal contribution from gravity. So if nothing would prevent you to lower B, you will find inconsistency with causality. And that means that, okay, then means that you cannot lower B arbitrarily. So there must be an impediment. This impediment means that some new physics must come by. And that's basically a statement that you see there's a cutoff in theory. So that's basically a statement was done in this fantastic paper here. It's twofold that the statement that was done, actually in a much broader context, is that if you, in a theory that these statements apply to our present discussion, if you have a plus vertex photons, that must be an effective theory. And of course, it's not surprising that we add an irrelevant operator, but I think it's still pretty interesting that you can formalize an argument, a sharp or clear, neat argument to derive this. More importantly, I think in this paper was pointed out that if the UV completion that has to come at some scale in order to prevent this causality violation, if that UV completion is at 311, then it cannot be some generic thing, has to be an infinite towers of eigenspin states, very much like you would expect in a stringy UV completion. So this is certainly very interesting, and it, it stirred a lot of attention and investigation further. To me, the most pressing question after this work was, or it is, that the fact that this assumption here seems pretty strong to me. When we look at an effective operator as a low-energy observer, it doesn't come with any label that says it's UV generated from 3 integrating out at 311 things, or it comes from some loops, or it's a couple or some couple. It seems you don't have control on this thing. So is the conclusion that you need infinite many eigenspin robust? Is this a structural properties? In particular, how things are going to change with loops? So that's the question they're going to answer, and how this is tied to the question of causality violation. So when you include loops, now it's important basically that the exchange of momentum here is getting larger as you decrease the parameter. You start resolving the structure of the energy momentum tensor, the matrix element, which we call the self-stress. Before, the helicity preserving term was a number, was Planck, 1 over Planck squared. Now is a function of the momentum exchange, and the same for the helicity flipping contribution is some form factor. And the Conal amplitude looks like this. So when you Fourier transform, it's going to take a different answer than before in general, when Q is lowered. Sorry, when Q is increased and B is lowered. So you will need to calculate this form factor. As a matter of fact, you need much less, because the Fourier transform actually will pick the discontinuities in the complex T-plane. And there are two types of discontinuities, the one from pole, from the gravitational exchange in T-channel. And then there are discontinuities associated to the multiparticle exchange in T-channel, and then they mix with the graviton and going to scatter and going to talk to the spectator field. So you need just basically to calculate on-shell amplitudes and integrate them over some phase space. And as a matter of fact, once you know the discontinuities of these form factors, you know the whole functions by using the special relations. And it's interesting that this is a nice observable. It's the energy momentum tensor for photons. You can calculate the full standard model That's going to give you the leading coupling to gravity at one loop. These are the limits for small momentum exchange or for large momentum exchange for the values for factors, depending on the spin of the particle that run in the loop. M is their mass, and alpha is coupling, is electric coupling square over 4 pi. So there are two interesting things here. So for small momentum exchange, the elasticity flipping contribution here, the one that was responsible for generating a possible causality issue with causality, as it frees to a constant, a small momentum exchange, and you can match it to alpha 3 in the effective theory. Okay, nice. Now a large T, this is the case like 1 over T, and it means that discontinuity as a delta function. And you can immediately, interpret this delta function as the presence of trace anomaly. In fact, you're calculating basically the dispersion, the dispersive kernel of the energy momentum tensor, and it contains the spectral density contains a delta function that's is precisely what you get in the chiral anomaly. That's precisely is the IR side of the anomaly, exactly the same you get for the trace anomaly. These F3 contribute, for example, to the trace. Now that you have these 4 factors, you can ask the question again: what's happening with causality if the UV completion enters a loop? So you do the Fourier transform of your scattering phase, you get the contribution from the pole here, associated with Q squared equals 0, the exchange momentum. So the exchange graviton in T channel, and that gives you the effective theory contribution at 0 momentum exchange, the log from minimal coupling, and the 1 over B square from the elasticity flipping contribution. But then you get the contribution also from the multi-particle state exchanged in T channel. That's what's coming from loops. And it has this form, is an integral in the Mandelstam variable T of some discontinuity of the 4 factors convoluted with some Bessel functions.
Brando, so, you have 5 minutes left.
Perfect. And this Bessel function decays exponentially at large when the argument is large. So when B is much larger than 1 over M, at the threshold of the multi-particle production in the channel, these just don't decouple, don't matter, you record the effective theory contribution. However, when B is lower, below the threshold of particle production, they are no longer exponentially suppressed. They are oscillating function that are no longer suppressed. And these two contributions actually adds up with effective theory contribution. One way to see what's happening is when you lower B so much that you can forget about the mass. So you can set the mass to 0 to get intuition what the physics here. And you see this branch point of the multi-particle production basically goes down, approaches the graviton pole. It gets closer and closer. Eventually, in the exact when you send B 0, that it touches it, and there's a cancellation between this term and this term. So in fact, the contribution from the elasticity flipping matrix elements was 1 over B squared from the effective theory. It's a contribution from the multi-particle states, and they actually cancel exactly up to a finite constant that's left over. And that's completely harmless, okay, from the point of view of the causality, because the leading term, which is logarithmically growing, is actually much larger than this contribution. So as is depicted here, so these are the contributional loops. As you lower B, so this would be the 1 over B squared behavior that would give you causality violation if it was continued. But in fact, as you cross the threshold of particle production, it goes to a constant. Interestingly, also there is a contribution coming from elasticity preserving matrix element of the energy momentum tensor that corrects this scattering phase even further. It gives you a log squared of B, the impact parameter, times the beta function associated to the particle running in the loop, so the QED beta function. And that's not, and it comes crucially with a minus sign. And it's no coincidence, it's not, sorry, accident that the beta function is appearing here, because there's a single operator, in fact, that reminds the contribution to basically contributes basically to the rounding coupling, gauge coupling, which is this one. The gauge is the kinetic term for the photon. but it is also the same operator that contributes to the elasticity preserving scattering of photons against the gravity. So in fact, you can normalize the electric charge in two complete equivalent ways. You can say, I scatter one electron again and exchange a photon at a certain moment to Q, a fixed electric charge that way, or you can scatter a photon exchanging a graviton with some moment to Q that also fixes the same electric charge. That's why the same beta function, the beta function appears here in the gravitational scattering as small impact parameter. You can make this argument, you can turn it, these words in a mathematical equation, which is the following. So basically the beta function is related to the gravitational force factor associated to elasticity preserving amplitudes at large momentum exchange. This discontinuity here. And you see that discontinuity appears in this kernel. That's no surprise that indeed shows up here. This is just a fun fact to say that you can calculate. This is actually a side product of our calculation is that you can calculate beta functions using completely on-shell data, not even related to gauge theory, just related to capping to gravity. So you just use gravity as a probe, calculate the force factors into gravity out of with on-shell methods, and you can start the beta functions from QED. Okay, so now this is the leading behavior as small impact parameter when you try to see what's happening, what would fix the issue, the causality, if it's not coming from infinite towers of Eiger resonances, but multi-particle states exchanging the channel. We get the log of B. That was a constant that I'm dropping, subleading relative to this one. They come from the elasticity preserving photons. L is log square B, gauge coupling, so loop factor basically expected, and then the coefficient from the QED beta function with a minus sign. So you see basically no causality violation all the way up to the Landau pole. And in fact, you can reverse the argument. You can still use basically that this has to be positive to determine that QED as an issue. So it's not a complete theory. Something has to come before the Landau pole. It's still basically, you can still, rather than using a very relevant operator and using causality to determine the existence of a cutoff, now you're using an operator which is marginally irrelevant, but still causality is able to capture an inconsistency of the theory.
Brando, could you wrap up?
Yeah, I'm done. So is Tower eigenspin generic? Well, I would say yes, but in this case, in a very trivial way. So you're still exchanging object with very large angular momentum, but this is just the pairs of electrons. They have large angular momentum. Is the orbital one that is making up for the contribution. So I'm going to skip something about the notion of causality. And here are my conclusions. Associated causality is indeed, I think, structurally robust, can even predict the existence of the Landau pole in QED, which would be a deformation of the free theory with an marginally relevant operator, and is still able to capture it. And this is true basically regardless of whether this higher dimensional operator are the generator tree or loop level. Nevertheless, it's not powerful enough, I would say. The story teaches us that it's not powerful enough to predict the detailed properties of the unit. So the infinite towers of eigenspin, you cannot tell as a knowledge observer whether they are going to be, stringy states, like some fundamental part, like resonances with I spin, Eiger and Eiger, or just mundane pairs of multi-particle states which are separated. And as a Q byproduct, I show you that you can calculate beta function basically for gauge theory is just by using gravitational scattering. Thank you very much.
We have time for maybe one or two quick questions.
So can you comment on the case of QCD where the beta function could be negative or changing sign depending on the fermions?
So, sorry, can you repeat that? I didn't hear you very well.
Speak up. Okay.
Yeah.
Just speak up.
Yeah, just try. raise your volume.
Can you comment on the case of QCD where the beta functions can have different signs?
Yeah, so great. So QCD, so we, in fact, I mean, we discussed a similar, so in our paper we discussed similar setting that we embed QED in a SU2 Young-Mills theory, which would have a negative beta function. So in that case, however, so it's more subtle because there are appearances of Sudakov infrared logs that makes the story a little bit more complicated. As basically, there is indeed a positive contribution to the time delay. So it will not signal any inconsistency. So it will not point to any cutoff, which should be any, because you will complete theory. However, there is also a contribution from double logs, Sudakov double logs, that you have to resum. And those actually exponentially suppress the amplitude. So in that case, what you should really look at more inclusive observables rather than single photon scattering. And if you want to take out all of those infrared effects and focus on the contribution from the beta function. And that's something that we are planning to do. And we just mentioned badly basically. But yeah.
Thank you.
Okay, thanks. Yeah, so just so we can stay on schedule, let's end this session here. Thank Brando again and all the other speakers of the session.
Just a quick announcement. So first copy is going to be out there.